This is AP Precalculus notes for topic 3.14, polar function graphs. In the last lesson, we were able to graph points on polar functions, and now we're going to graph the entire function themselves. So it's hard to graph functions. Luckily, on the AP test for Precalculus, you'll never be asked to graph a function. It is super helpful to see how a calculator thinks, how a graphing calculator thinks. So we're going to pretend that we're a graphing calculator and do one hard problem, and then we'll use that analysis to help us in the future. So we want to graph this equation, that 3 minus 3 sine of theta. So we need a theta, an input, and our output is going to be the radius. And it's kind of a lot of work to do all these. I've done them in advance, so we can just write them all down. So when you plug in 0 into theta, sine of 0 is 0, so 0 times 3 is 0. This whole thing is 0, and 3 minus 0 is just 3. So you can go through all of these and just kind of copy what I have down. I'm going to go through things a little bit more thoroughly in Desmos to show exactly how your graphing calculator thinks and how you should be thinking as well. So go ahead and copy down the following values. We have 1.5, we have 0.8787, that was a lot of space there, whatever. We have 0.4019. We have 0, and then there's kind of this axis of symmetry here, so it's kind of the same problem, or same numbers back the other way. So now I'm going to say 0.4019, 0.8787, 1.5, and 3, and then we go even further. We say, okay, so now it's going to be 4.5, 5.1213, we have 5.5981, we have 6, and then that's kind of the axis of symmetry because 6 is as far as we can go. And it's the same numbers back all the way down to 3 again. So here we go. It's going to go 5.5981, 5.1213, 4.5, and then all the way back down to 3. So graphing this thing is tricky because this graph is split up not by counting by 1, 2, 3. It's kind of cut into thirds, which is ultra confusing, which means if I'm looking for graphing 0, 3, I have to have an angle of 0, so come out here to the right. And by the way, you can sometimes come out here to the left also if I have a negative value, but I have a positive value, so I'm going to be going out to the right, and I need to go out a distance of 3. Well, it's halfway between 2 and 4 is this spot right here, which is randomly not on any sort of line, so be careful. 1.5 at pi over 6. Remember that this line and this line we don't use because those are units of pi over 12. We have pi over 6 here. We have pi over 4 here. We have pi over 3 here. But we don't use that line or this line, right? So going to 1.5 when I go to pi over 6. So pi over 6 is here. 1.5, okay, well, 1 is right about there. So let me make a note that that's 1. 1.5 is halfway between this line and this line, which is going to be right about, let me make this in a different color, right about there, I want to say. So that's 1.5. I have to come up to pi over 6, which is right about there. And then now I have to go to pi over 4. So pi over 4 is 0.87. So it's a little bit less than 1. Again, you don't have to be super accurate about this. I just want you to see exactly what's going on. So it's a little bit less than 1, and I happen to know that 1 is that point right there. So it's a little bit to the left of that. And I'm going to say that's that point right there, sure. And then we go down to 0.4. So it's like half of 1. Half of 1 is like in here. Coming in here to pi over 3, and that's going to be right about there, I want to say. And then we finally get all the way to 0. So we go back to the origin. So luckily we have this axis of symmetry, which is the same thing as saying an axis of symmetry here. We have that same curl there. We're going to have that same curl out here. So just trying to copy it down to the best of your ability. Again, remembering to skip this line because we don't use that one. I'm going to come to a point right there. And then the next one is going to come out a wee bit right there. These points are way too big. I have to make them smaller. And then it comes out about right there, I think. And it comes all the way out to halfway in between here and here, which is right there. Okay, so I have the top half. Let me go ahead and try to sketch a line that goes through all of these points. If you do a lot of tiny little lines when you're sketching, it does make it look better, I think. Maybe you're able to freehand this without picking up your pencil and you're better than me. All right. So from here, I need to do the bottom half of the graph. So that starts with our 7 pi over 6. So at 7 pi over 6, again, that's not this line, it's this line right here. I have to come out to 4.5. So where is 4 again? Well, 4 is this line right there, and 6 is this point right there. So I would say 4.5 is right about, well, that's 5. So 4.5 is right about this point right there, I want to say. So I'm going to come down to that point right there. And then 5.5 is only a little bit more than that, and it's the next line over, so a little bit more than that is probably right about there. Next we have 6, which means I go to 3 pi, wait, 5.12, I think I've made a mistake. Let me make sure. So 4.5, I got my 4.5, okay, that was 4.5, then 5.12 is a little bit more, and then I do, yeah, there we go, 5.5 is this point down here, which is a little bit more. It's getting really close to 6, so getting really close to 6, I'm gonna say like that point right there. And then I go all the way to 6 down here when I get to 3 pi over 2. And then again, kind of use the axis of symmetry and say, okay, it's going to be right about there, and what do I want to say? Right about there. And you do your best to connect your points. Not my best graph of my life, I'll be honest. All right. And you come down like that. So it kind of looks like a heart shape. These are known as cardioids. I wish I could graph that a little bit better, but it's nice to see what this graph should have looked like. So let's use a graphing calculator. So with a graphing calculator, you can just say, really what I'm typing down here is if you want to do this on your own and go to like Desmos, you can say like R is equal to some function. So in this case, I'm doing 3 minus 3 sine, you can type in a sin of theta, sine of theta, like that. And you can see that it does indeed make that graph that I can turn on and off. So that is the correct graph. This is how you can graph it on your own. I have some cool extra features in here, so you can think about what's really going on here. So what's happening on the graphing calculator and what you need to be thinking of is there's this star that you can drag through. And this, you always start at 0 unless you have something weird happening. And then you're trying to figure out where this point maps to as you're slowly scanning through the space. Eventually we get up here to pi over 2, which meant we got back to 0. And then you're slowly scanning through space, trying to find every single point on this line. I'll show you why this is useful in a little bit. But for now, just think about a line that's sweeping through space. Once we throw in some negatives in here, it becomes extra confusing. Cool, so we know how to graph. And again, basically make sure you use your symmetries, because almost everything is gonna have symmetry whenever we're doing polar functions. All right, so this is the explanation saying, hey, everything is gonna be multiple choice, use multiple choice test taking strategies. So for example 2, let's show you how I would do that. Which of these is the correct equation of this graph? The very first thing that I see for my multiple choice is everything has a 3 theta in here. Usually that's a giveaway, because if you have like a 3 theta, that means that there are 3 branches, 1, 2, 3. I don't know if they're actually called branches. They're probably called petals or something cool, because it looks like a flower, right? And that doesn't help me. I have to figure out if it's sine or cosine or anything like that. So just plug in a value that you know and is nice. So this value right here is terrible because I have no idea what that value is. Maybe it's 2, maybe it's a little bit more than 2. Here's a better value that I can plug in. This value right here is on what I'm considering a lattice point, because I come all the way out to a distance of 3, and I know that this value here is pi over 6. So I know, hey, if I plug in pi over 6, I should get out a 3. That's what has to happen. All right, so let's think about this. If I plug in pi over 6 to any of these, I'm going to first multiply by 3. And if I do that, pi over 6 times 3, that's going to be pi over 2 when I cross cancel, because the 6 and 3 cross. So pi over 2. I need to have a value of essentially 1, and then I'll multiply by the 3. Notice that if I plug into a cosine of pi over 2, when I plug in my pi over 6, I will get a pi over 2 on the inside. Cosine of pi over 2 is 0, because again, pi over 2 is right here on the unit circle, and I guess the unit circle is this circle right there, though. If I plug in pi over 2, I get 0. I do not move to the left and right, which means this whole thing is going to be 0, and 0 times 3 is 0. This point is not 0 there, though, so cosine is out of the running. You can immediately eliminate options C and D. That's the test-taking strategy that I was talking about. So now you just have to decide between these two options, and it's pretty straightforward, again, by plugging in pi over 6, which outputs a pi over 2 on the inside, because when we do that, this is going to evaluate as 1. These are both just 1. So 1 times -3 is -3, and I would have come to the other side of the graph down here to this point, which is not on the graph, obviously. I just have a positive 3. I'm going in the positive direction, and therefore the answer here is A. And that's one of the things that you really need to think about, because what's happening is you have that line that's slowly mapping its way through our function. This function was easier because it has a positive. And the next one, I'm going to use Desmos to show you exactly what's going on. Maybe not example 3. In example 4, I'll definitely be using Desmos because it gets really confusing. All right, test taking strategies again. We know that we're graphing between 0 and 2 pi. We're trying to figure out which of these equations is correct. So you'll notice that when I plug in a value that's nice, I want to say that that value is nice and that value is nice. I'm using like air quotes right now that you can't see. I know that that value is probably 3 pi over 2. But the question is, are these both points 3 pi over 2? Because that's not a function. A function says one input goes to one output. Does it go to that one or does it go to that one? And there's a question on which one it goes to. And that's because you have weird negatives happening. Because you'll notice, even in the last problem, right? There's like this dead man space. Like what happens up here? Like if I plug in pi over 2, do you get 0 or do you get something else? And here, maybe it's worthwhile talking about this right now. Watch what happens when I plug in pi over 2. It has to scan through the space. So let me enter 3 sine of 3 theta into my function. So if I come up here and edit, 3 sine of 3 theta gives this function. And check it out. When I scan through space, it makes sense because it comes all the way up through here. The question is, what's going to happen when this star value that I'm dragging around goes to pi over 2? And I really want you to make that prediction. When I come up here to pi over 2, it goes through the graph and keeps going onto the other side. So check it out. This star is at pi over 2, but the point on the graph is on the bottom half because I have a negative value. And this is because when I plug in pi over 2, and I multiply it by that 3 theta on the inside argument of sine, I get 3 pi over 2, which is pointing straight down. Even though my star is up here, I can have something on the entirely other side of the graph. So every time that you see some like empty space, you need to be thinking, oh, I went to the other side of the graph and it's talking about this pedal down here. In fact, when you make one revolution, if I drag the star to this point, I will hit every single point on this arc at least one time. And then when I go the second revolution, I hit every point a second time. I mean, just check this out, right? So watch me, this point on the graph is gonna hit every single point on this graph once and go all the way back to 0 by the time I hit pi. But notice I still have to drag it all the way around to 2 pi and it does the same exact trace a second time. Sometimes that happens. It usually happens when you have like odd numbers as your argument on the inside that's being multiplied by theta. If you have like even numbers, interesting things happen. But again, I don't want to get too in depth here. This is not an AP Calculus BC class. This is just pre-calculus. So let's do example 3. And now you kind of have an intuition of like, oh, I have a dead man space up here. I don't know what happens when I plug in any value up over here. And the answer is, oh, that's because it's this piece probably right here. Or maybe it's that piece, but most likely it's like that tiny piece. Let's see what happens. Again, plug in a test value. I happen to know that 3 pi over 2 is either going to be that point or that point. It's going to be some nice value. It's either going to be 2 or it's going to be 6. So let's plug it in and see what happens. When I plug in 3 pi over 2, let's just test option A, right? That's going to be sine of 3 pi over 2. And I happen to remember that my unit circle, 3 pi over 2 is down here. Sine is the y-coordinate down here is a -1. So this entire thing is going to be -1. -1 times 4 is -4. -4 plus 2 is a -2. And that makes sense, right? That ended up being that value right there instead of that value right there. When I try to point straight, or wait, no, that's not right. So if I point straight down, I was expecting to get either this height or this height. Instead, I got a -2, which meant if I'm facing down, I go -2 backwards to this point right here, which is not on the graph. This is the point that we should have graphed because I was pointing down at 3 pi over 2 and my answer said go -2 for my radius, come back to this point. So A is actually eliminated. Let's try it again with another value. So let's plug in 3 pi over 2. Again, I'm pointing straight down and I'm asking which of these 2 points am I going to hit? I have to hit either one of them and I'm technically on the graph, right? So if I plug in 3 pi over 2 to this sign, again, I know that this value is going to be -1 just like it was last time. 4 times -1 is -4 times a negative is a +4 and a +4 plus a 2 is 6. If I'm facing down, I can go 6 units down and that is a point on the graph. So this one is still in the running. You have to keep doing them with all of them. 3 pi over 2, plug it into theta, right? I'm pointing straight down. Where do I end up? If I do that, cosine of 3 pi over 2, again, on the unit circle, 3 pi over 2 is right here. Cosine is how much left and right I'm moving. I'm not moving to the right. I'm not moving to the left. Therefore, this value is 0. And 0 times 4 is still 0. And then 2 plus that 0 is 2. And when I'm facing straight down, I go 2 units. That is a point on the graph. These are both points in the graph. So I haven't decided between B and C. I'm hoping that D is going to be eliminated. Let's go ahead and test it. Okay, again, face straight down, plug in 3 pi over 2, and I'm going to plug that in over here. Again, cosine of 3 pi over 2 is 0. 0 times 4 is still 0. And then 2 minus 0 is still 2. Okay, so I've really only eliminated A by choosing to point straight down. What's another value that I can choose? And I'm looking at that one right there. That one looks really nice. Now, if I plug in this value, if I point out to the right, if I point to my theta is equal to 0, straight out to the right, I should get out a 2. Let's see what happens, right? Maybe that was a better point. I should have started there. If I plug in 0, 0 on my unit circle is pointing out to the straight right. I can say, okay, plugging in 0 for theta, sine of 0 is 0. So this entire thing is 0, and 2 minus 0 is still 2. Okay, so this one is still in the running. It made it. Let's plug in 0 again to the next one. When I plug in over here, cosine of 0, cosine is the x-coordinate. I've moved right 1, so cosine of 0 is 1. 1 times 4 is 4, and 4 plus 2 is 6. This whole value is 6, and I did not come out 6. I came out only 2. So now option C has been eliminated. Maybe 0 will be the magic bullet. Let's go ahead and plug in 0 over here as well. Cosine of 0. Again, cosine is x-coordinates. This is 1. 1 times 4 is 4, and 2 minus 4 is negative 2, which technically is on the graph, right? If I'm pointing in this direction, I go negative 2, that means I'm going negative 1, negative 2, and I'm going to this point, which is on the graph. So we can't eliminate D. We need some other value. And I'm trying to figure out what is a good point to test that will definitely distinguish between these two graphs. I don't really have any good ideas. I guess we can just plug in that one and see what happens. I have a feeling that that one's going to switch to that one. I don't know. Let's go ahead and test it. We're going for it, guys. All right, so now I'm pointing at this direction, which is pi. So pi is my new guess. So on my unit circle, pi lives right here, and I'm theoretically supposed to get out a positive 2. If I'm facing this direction, I should come out positive 1, 2 units. So let's try it. Plugging in pi for this theta is going to be sine of pi. Sine of pi is how much up and down I'm moving from this point in the unit circle. I'm not moving up, I'm not moving down, therefore this entire value is 0. And 0 times 4 is 0, and 2 minus 0 is still 2. So yeah, I did move 2 forward. Okay, that is still in the running. Let's go ahead and plug it in here and cross our fingers to the math gods. Oh, please let this work. Okay, when I'm plugging in pi over here to theta, cosine of pi is, again, cosine is how much I'm moving left or right. I'm moving left negative 1. So this entire thing is negative 1. Negative 1 times this negative 4 is a positive 4, and positive 4 plus 2 is 6. This whole thing evaluates as 6. Well, when I'm pointing to pi, I'm not going out 6. I'm only going out 2. Therefore, D has now been eliminated. Whew. And you can see that if I had maybe chosen to start at this point, that might have been really the magic bullet that probably eliminated all of these in one go. But sometimes you just have to do guess and check. Just plug in points and hope that it works. Choose nice lattice points. I chose this one. I chose this one. I could have chosen this one. I could have chosen this one. There aren't any other really nice lattice points on there. So I'll circle the ones that I could have used. I could have used the ones that I used. There, and there. And then these two also could have been used. So that's a lot of checking though. So choose whichever one you think is going to be the best. Sometimes you guys have better intuition than I do. All right. Example number 4. This one is super tricky. So we're not trying to figure out an equation anymore. We're restricting the domain. So here's how it phrases the question. Hey, we know the function. The function is negative 3 sine of theta. And that negative is going to really be tricky. So whenever you have a negative out front, what that does to a polar graph is it rotates everything 180 degrees. So if you think you're starting at 0 and you're doing that scan where that line is coming out and then moving this direction, you're wrong. It's actually starting in this direction and then scanning from pi this direction, even though it's technically starting at 0. So that does make it difficult. So we need to figure out what is being graphed here. What is the correct domain restriction? And really, you can just eyeball these. You don't really have to do a lot of hardcore math here. So technically, this is pi, but now that we've rotated 180 degrees, this is now 0. I'm starting from this line and I'm moving in this direction because I have this negative out front. You can also call this a reflection over the origin, but that's the same thing as a rotation of 180 degrees. So I'm going to start here. I'm going to keep moving. And where's the first time that I hit a point on this curve? Well, right here. And that happens how far away? Well, I've rotated. You still are rotating clockwise, right? That hasn't, or counterclockwise. I apologize. You're still rotating counterclockwise. I've rotated how much counterclockwise? Well, I've rotated now pi over 2. That was a terrible 2. Pi over 2. And then now I've started hitting the function. I don't know if it's hitting it there or there when it's sweeping through, but I know that it's probably doing either that or it's doing that when it's rotating out. In fact, I can tell what's going to happen. It's probably starting here, and then as it comes in further, it's sweeping farther and farther out until it hits pi, and then it ends right here. So I'm going to say it goes between pi over 2 to pi, because that's what it visually looks like after I rotate it 180 degrees from having that negative. So my answer is going to be from pi over 2 to pi. That's going to be option B. And here's how I'm going to check my work. I'm going to use my calculator. So this function, I've already forgot what the function is. The function is -3 sine of theta. Oops, -3 sine of theta. So I'm going to put a -3 sine of theta. And okay, yeah, that makes sense. So notice that when I'm still dragging the point normally on my function, and notice that when I start dragging the star around, it moves out to the left. You would think that the point should be more out to the right, but it's been rotated 180 degrees. So it comes all the way out, and then by the time I hit pi over 2, boink, that's pi over 2, right? And then this star is going to drag from pi over 2 all the way to pi, and notice where that point on the graph is touching the curve. It's touching the curve exactly in the section that I was talking about earlier. Therefore, pi over 2 to pi is indeed the correct answer. All right, let's try another one. All right, so I'm seeing from the get-go, we have a 3 theta on the inside. So that means I'm going to have like 3 petals. I'll have a petal there. I'll probably have a petal there. I'll probably have a petal there. Oh, whoa, no, that's not correct. Okay, I'm going to have like 3 petals, probably there, there, and there. And then this 3 is just going to make everything come out 3 as opposed to out 1. It's changing the amplitude of everything. Okay, so we have a domain restriction in place, and this one is even easier. There's no negatives. There's no rotations. There's no reflections through the origin. So you see what you get. So I happen to know that this is pi over 6, this is pi over 4, this is pi over 3, this is pi over 2, and this is 0 down here. Again, we ignore these lines and these lines because we don't do the pi's over 12s or the 5 pi's over 12 or anything like that, right? So where is this line? That's all you have to do. Eyeball it. Which of these lines is the true domain? And I would say I'd never even get to pi over 4. It never even touches that line. I mean, it gets close. It really ends at this line right here. Just visually look at it. This is the line that's kind of like the asymptote. It gets closer and closer to that line, but it never actually touches it, which means we were scanning between 0 and pi over 6. That we're done. That's all we had to do. So where's 0 and pi over 6? There it is. 0 and pi over 6. The correct answer here is D. Again, just to double check my work, let's plug in 3 cosine of 3 theta on my calculator and see what's really happening. So if I go over here and I type in, please, there we go, 3, please, thank you, 3 cosine of 3 theta. There it is. Again, let's move the star all the way back to the beginning. And you can see that I'm just dragging between 0 and pi over 6. After I hit pi over 6, where does the function go? It continues. You always have that smooth motion. It continues onto the other side of the graph because I have negative values. And then it keeps continuing. It's just kind of fun to watch. And by the time I hit pi, it goes all the way back to where we started, which is all the way back here. Nice. Okay, so we were correct. It goes from 0 to pi over 6 because after pi over 6, it goes here and then it comes out like that. And then up like that, and then, okay, not the best graph of my life, but we can see that we were right. Moving on to our final example for the notes, example 6. Okay, so this one is really interesting. So we know the function, again, so we can check our work. And it says, hey, we already know the domain restriction. Here it is. It's between pi over 3 and 2 pi over 3. Okay, graph that. Where is pi over 3? Where is 2 pi over 3? That will give you kind of the answer to this question. So pi over 3 is not you, not you, not you, not you. Oh, it is you. It is you. Okay, so it's pi over 3. Pi over 3. Again, we ignore this line and we ignore that line. So pi over 3, so it's right there. Now I'm noticing this is like a dead man zone, which means pi over 3 was really all the way on the other side. That's really the pi over 3. I probably had a negative value for C. And then I go all the way to 2 pi over 3. Okay, so 2 pi over 3 is this value right there, 2 pi over 3. So I obviously have a positive value when I'm scanning through this area because I'm touching my graph. Because really what I want to do is I want to say, okay, everything between this line, let me make this a little bit thicker. I can say everything between this line and this line is fair game. The problem is I have like a no man's land on that section, which means it's on the other side of the graph. So let me go ahead and extend that line all the way, like, okay, not the best line of my life here. Let me make you go better, which means I have everything from when I'm scanning this line this direction, it means this line is going this direction. It's talking about this curve right there and this curve right there. So let me highlight that. That's really the answer for this problem. This is the line that it's talking about. That section of the line is what we're talking about between pi over 3 and 2 pi over 3, because pi over 3 is here, which means we have to be on the other side, and then we scan all the way until we hit 2 pi over 3. Let's read the rest of the question. What are we asked to find? It says, hey, the portion of the graph remains consistent of two pieces. There's two pieces, I guess. Okay, one of those pieces is in quadrant 3, so it goes quadrant 1, quadrant 2, quadrant 3. So it's talking about this quadrant 3 from C to D. Okay, well, C is here. D, I kind of wrote over it, but it's from C to D in quadrant 3, and it's not going from here to here. It's going from here to here because I can see where I've highlighted. So that's the section that we're talking about right now, and it's asking which of the following describes the remaining piece. Well, I already highlighted the remaining piece. The remaining piece is right there, which is between D and A. And that's in quadrant 2 up here. So we want to say quadrant 2, D to A. The correct answer here is C, just being able to read the graph. And again, we can check our work. So let's go ahead and go 6 cosine of 3 theta. So we'll type in 6 cosine of 3 theta. Is that the exact function? Did I get it right on the? Oh, nice. Okay. And from here, I'm going to figure out what happens when I go to, I think we start at pi over 3, right? So pi over 3 is that point that I just talked about, and it's going to scan all the way through until we hit 2 pi over 3, which is right there. And you can see where that point in the graph highlighted. It went from here and it went to there. Cool. So I definitely got that question right. If you guys are curious about this Desmos calculator, it's not anything fancy. It's some stuff in here that I just made a few minutes ago. If you want to use it, I will link it to the YouTube description so you can click on it and play with it. That does conclude the notes for topic 3.14, polar function graphs. Guys, we only have one more lesson, at least as of 2025, left in this curriculum. So we're almost there. Let's go ahead and look at all the notes. So last page and then second last page, second page, and the first page. Thank you for watching.